In the previous video, I introduced the statement of the first part of the fundamental theorem of calculus, and I showed some examples of how to use it. In this video, I will write down a proof for the theorem. As a reminder, here's what the theorem says. We begin with an interval I, a fixed real number a in I, and a function little f defined on I. And we define a new function, big F, which is an integral of little f. Big F of x is the integral from a to x of f of t dt. And the theorem says that if little f is continuous, then big F is differentiable and the derivative of big F is little f. Or in other words, a function defined as an integral is an antiderivative. The proof of this theorem is perhaps a bit long, but it is not too abstract. Let's begin. First, I am going to fix a real number x on the interval I. So for the purpose of the proof, both a and x are fixed constants. A was already fixed in the statement of the theorem, I'm fixing x now. And I am trying to prove that the derivative of f, big F at x, is little f at x. Let's use the definition of derivative as a limit. We know that the derivative of big F at x is the limit at h approaches 0 of f at x plus h minus f at x divided by h. This is just the definition of derivative. And then let's use the definition of big F as an integral. So I'm separating the 1 over h, and what I get is the limit at h approaches 0, 1 over h of the integral between a and x plus h minus the integral between a and x. That was just using the definition of big F. And an expression like this is primed to use a common property of integrals. The integral from a to x plus h minus the integral from a to x is the integral from x to x plus h. The only thing I've done so far is use definitions, and I have concluded that this is an expression for the derivative of big F of x. So what I am trying to prove, what I want to show to conclude this proof, is that the limit as h approaches 0 of 1 over h times the integral from x to x plus h of little f is f of x. That's my objective. It is going to help to look at this geometrically. So let's draw a picture with all of this. Here I have some axes. I'm using y and t as the coordinates for the function little f. And here is its graph. I have a fixed value of a and a second fixed value of x. And then x plus h will be another number, for example, this one. In this picture, the integral from a to x of little f is this green area. And the integral from a to x plus h is this green area. And yes, we know that the difference between both of them, this smaller green area, is the integral from x to x plus h. Okay, so now we have a geometric interpretation of this. And let's recall what we're trying to do. We want to show that if I take this green area as a function of h, I divide it by h, and then I take the limit at h approaches 0, that is equal to f of x. Well, I'm going to take a limit as h approaches 0. So let's see what happens when I take smaller values of h. If I take a smaller value of h, a smaller one like that, and even smaller, this is what happens to the green area. And I'm observing that for small values of h, the slice of green area can be approximated by a rectangle. This is not precise. I'm going to make it precise in a moment, but for now it's more or less a rectangle. And it's a rectangle whose width is h and whose height is about f of x. Is about f of x. This is not precise. But what I'm saying is that if h is small, the green area is about f of x, the height, times h, the width. And therefore, the green area divided by h is about f of x. This is an approximation when h is small, and it will be a better approximation the smaller h is. So this looks good. Therefore, probably when I take the limit as h goes to 0, this won't be an approximation but exact, and that's exactly the limit I was trying to compute. But this is not rigorous, so let's make it rigorous. Going back to the picture. Instead of saying I approximated by a rectangle, what I can say precisely is that the green area can be bounded above and below by rectangles. It can be bounded above by a rectangle whose height is the supremum of the function, and it can be bounded below by a rectangle whose height is the infimum of the function. This is similar to what we did when we defined definite integral. So, algebraically, I'm going to assume for a moment that h is positive. We should be looking at h positive and negative, non-zero. And I could try to use notation that works for both, but it is simpler to use a notation only for positive. So maybe we should do a proof for positive h, the limit on the right, and then a separate proof for negative h, the limit on the left, but the two are very, very similar. So I'm just going to focus on positive h and do only that. So I'm going to give names to this supremum and infimum. I'm going to call big M sub h the supremum of the function between x and x plus h, and little m the infimum. And then I can say that the green area, the integral from x to x plus h, is at most big mh times h, and at least little mh times h. Or, if I divide by h, the function whose limit I'm trying to compute is sandwiched between little mh and big mh. And now we're getting close. Look at the top at the thing we're trying to prove. We're trying to prove the limit of this function of h is f of x. And at the bottom, I see that this function is sandwiched between two other simpler functions. So this makes me want to use the squeeze theorem. If I'm able to prove that the limit as h approaches 0 of big mh and little mh is the same thing, then the limit of the thing in the middle will also be the same thing. And that will conclude the proof. That will be everything I need to do. So can we do that? Can we prove that those two limits are f of x? Yes, it's going to work. And here is why. First, notice that f is continuous. So by the extreme value theorem, it has a maximum and a minimum on this interval. So we're not talking about suprema and infima. We're talking about maximum and infimum only. So since it has a maximum, I can say that big MH is just the maximum, not the supremum. And therefore, big MH is f of something. I'm calling it something c sub h because it's going to depend on h. As I change h, the point where the maximum is reached changes. So more precisely, I should say that there is a value of ch, a real number between x and x plus h, such that the maximum, big MH, is f of that. And to be precise, this happens for every h, and c sub h depends on h. Okay, so now ch is between x and x plus h. As I make h approach 0, ch is going to have limit x necessarily, and therefore f of ch is going to have limit f of x because f is continuous. That's fundamental. If f were not continuous, the theorem would be entirely false. So that's exactly what I wanted. And now if I put together what we have, we are pretty much done. So let's finish the proof. We had gotten to this expression. This function of h, 1 over h times the integral from x to x plus h of little f, is sandwiched between little mh and big mh. And little mh and big mh have the same limit as h approaches 0, which is f of x. Therefore, by the squeeze theorem, the function in the middle also has limit f of x. But that is exactly what we wanted to prove. And this completes the full proof of the first part of the fundamental theorem of calculus. The second part will be easier. Well, that was long. I think I need some chocolate.